And welcome back to part two, ladies and gentlemen. We're going to be continuing with our discussion on energy and chemical reactions. We started last time with this figure and said that our reactants have a certain amount of energy that they contain, potential energy, and then the products also have a certain amount of potential energy. And in almost every single chemical reaction, the potential energy of the reactants and the products will be different, and we can account for this difference. So knowing whether energy is released to make products or whether energy is absorbed to make products, we can get exothermic and endothermic reactions. So we have some definitions here to help us communicate. That matter contains kinetic and potential energy, right? The potential energy of the reactants is different from the total overall potential energy of the products. And this difference in energy has to be accounted for. It has to either transferred to the surroundings or transferred from the surroundings because the first law of thermodynamics says that energy is conserved. Energy can be neither created nor destroyed. So we had a lot of these conservation laws in physics. We have the conservation of mass, which we used to help balance matter in atoms in an equation. Now we also have to balance energy in equation or a reaction. So we basically have two possibilities that the products are lower in energy or the products are higher in energy than the reactants. So that difference in energy is often converted into heat energy. So one thing that can happen, we'll focus on the left first here, is heat can be released to the surroundings. So this would be an example of the products. Here's my reactants, and here's my energy. Products have lower energy than the reactants, so they release energy to the surroundings. The surroundings get warmer. This is called an exothermic reaction. So if we actually look at this word, it'll help us remember it. So exo is like exiting. It's out of. Exo means out of. And thermic is like thermal energy, right? Thermal heat. So heat is out of the system. Heat is leaving the system into the surroundings because the reactants have higher potential energy than the products. Now on the right hand side, we can have the opposite case, right? If heat can be absorbed from the surroundings to make the reaction go, the surroundings get cooler. So if we have an energy diagram here, the products would be higher in energy than the reactants. The reactants would be lower in energy than the products. And this is called endothermic. So endo is like inside, right, or into. So heat into the reaction. So these are endothermic reactions. So if we go back to that first example, right, is this exothermic or an endothermic reaction? The potential energy of the reactants is higher than the products, right? So this is heat being released or out of the system. So this is an endothermic reaction. Okay, other forms of energy can be transferred during a chemical reaction as well. So in a car engine, consider that gasoline is a molecule or multiple different kinds of molecules, right? It's combusted and energy is released through that reaction. So some of that energy is converted into mechanical energy to propel the car forward, right? That's why we have it there, right? Um, so some of that potential energy is converted into kinetic energy to make the car go forward. Some is also still transferred to the surroundings as heat, right? If you touch your engine after driving, it would be hot, right? Because it does produce heat, but that's because it's an exothermic reaction. Another example is a biological cell, as we saw in the previous slide, right? The glucose undergoes combustion, same kind of combustion reaction, right? It reacts with oxygen, and energy is released. So some of that is transferred as heat, but also most of it is transformed into other usable forms of energy for the cell, right? It's a part of a process that allows your body to move and continue living. So ultimately, we're just talking about energy in general, and heat is one form, but it could also be transformed into kinetic energy or other forms of energy. So one way that we can quantify the energy of a molecule is to talk about the bond energy. So a molecule has bonds, and a chemical reaction is bonds breaking and new bonds forming. And bonds themselves have potential energy, like holding it together, right? And when atoms bond, the potential energy of the atoms decreases. That's why they bond. It's actually it's a more stable set if they're bonded together. So typically, making a bond is exothermic, right? Because it decreases the potential energy. So the reactant would be two separate bonds. The product, or sorry, two separate atoms. The product would be two atoms bonded together. It lowers the energy, so that means that it's exothermic and it releases energy. Which means breaking a bond requires energy. Breaking a bond is endothermic. You have to put energy into it to break it. So if we look at a combination of bonds breaking and new bonds forming, we can determine the net change in bond energies. Because bond energy is defined as the amount of energy required when breaking 1 mole of a given bond type. Now, conversely, it's also equal to the amount of energy released when making 1 mole of a given bond type. Okay, so we can define it either in terms of energy input to break or energy output to make, and be the same value. We'll look at those values in just a moment, but first, here's a question. So select the false statement about making new bonds. Why don't you pause it and think over what we just talked about in the last slide, and come back when you have an answer. Okay, actually, I realized that part E, we haven't talked about that yet. That comes up in just a few slides, but that is actually true. So you can ignore that one or say that that's not the correct answer because that is true. So we're trying to find the false statement. Delta H for bond making is less than 0. That is true. So the false statement here is this one. It takes energy to make new bonds. So remember, to make new bonds releases energy. To break bonds requires energy. So that one is false. Let's check that the other ones are true. Energy is released when bonds form. Yes, that's true. Bond making is exothermic. That's saying the same thing. Energy is released. Yes. After the bond is made, the atoms connected to the bond have lower potential energy. Yes, that's why the bond forms. And delta H is negative. Yes. So this D is incorrect. It releases energy to make new bonds, or you could say it takes energy to break bonds. So let's look at the energy that is required to make and break bonds by looking at the average bond energies of some representative bonds. Okay, and let's focus at here where we have similar bonds where the only thing changing is the single bond here, CC single bond, CC double bond, CC triple bond. So the same atoms involved, but changing bond strength. And notice that the bond energies increase, right? So a stronger bond, like single up to double, up to triple, get stronger, correspond to higher bond energies, right? That means that it takes or it releases more energy when that bond is formed. So it's more stable, it's lower in potential energy. It's hard, it's like in the bottom of a deep well. It's hard to get out. It's a very stable, strong bond. We have a higher value here. Weaker bonds correspond to lower bond energies. Therefore, it's higher in potential energy. It's easier to break than the other ones. Another series you can look at here is this OO single bond and an OO double bond, and you see the same pattern, right? That the double bond has a higher bond energy. So it's a stronger bond. It takes more energy to break it, or also it releases more energy when it is formed. Okay, so we can look at all of the bonds in our reactants and the sum of all of the bonds in the products and determine what we call the heat of reaction, or the overall delta H. That was from that last question, delta H, which is the amount of energy released or absorbed during a chemical reaction. And it is an equation that we have, right? It can be equal to the sum of all of the bond energies of bonds broken, which would be the reactants, minus the sum of the bond energies of the bonds formed, which would be all the products, right? So if delta H is negative, then that means that the products are more stable, right? That the bond energies add up to a greater value than the reactants, and it's exothermic. It releases energy when it forms. If delta H is positive, then the reaction is endothermic. Okay, let's look at one example before we end here. Sorry, let's do two examples. So here's a reaction. It's balanced. It's the combustion of methane. So we have CH4 plus 2O2 makes CO2 and H2O. And this is exothermic, right? It's a combustion reaction. It gives off heat. Let's look at this reaction and the delta H of reaction and calculate that. And use the bond energies to calculate the delta H of reaction. So first we need to look at what bonds and bonds energies are present in the reactants. Okay, so we have CH4, which is a CH bond, right? And there are 4 of them, right? So we have 4 CH bonds. And then O2. O2 is it's a double bond. And if you go through the Lewis structure process, right, you can determine that it's a double bond. And the coefficient here tells us that there are two O2 molecules. So we have 2 OO double bonds. What bond and bond energies are present in the products? Well, we have CO2. Again, if we remember our Lewis structures, CO2 is like O2 with a carbon in the middle, right? And so we have how many CO double bonds are there in a CO molecule? Well, there are 2 bonds, right? Because here's a CO double bond and here's a CO double bond. So we have 2 C double bond O. And then water. Water would look like this, right? A bent molecule. And each water molecule has an OH and an OH. And there are 2 molecules, so we have 4 OH bonds. Right? Now, let's look at the bond energies present. So a CH bond has a bond energy of 414 kilojoules per mole, and we have 4 of those. An OO double bond is 498 kilojoules per mole. We have 2 of those. So we can look at the total bond energy of the reactants, just 2652 kilojoules per mole. We can look now at the products. We have a CO double bond, which is 799 in CO2. So we have 799 times 2. And then an OH bond is 464, and we have 4 of those, for a total bond energy of products to be 3454 kilojoules per mole. Okay, so we see how some of the past is still important, right? We need to be able to look at a molecular formula and know the Lewis structure. Right here, molecular shape is not important, but how the atoms are bonded and arranged with each other, which is the Lewis structure, is important. And then we get the total bond energies of reactants and products. And here in the next slide, we'll repeat what we just had. So here's the reactants, 4 CH bonds, 2 OO double bonds, products, 2 CO double bonds and 4 OH bonds, and then delta H of the reaction is the sum of the bond energies broken, which is reactants, minus the sum of the bond energies formed, which is products, and it gives us an overall negative 802 kilojoules per mole. So we said negative means exothermic, which means energy is released. And so this is a combustion reaction. Energy is released. It's exothermic, right? I have one more example, but this one is already given and we'll just walk through it. So let's say you used electrolysis to convert water into hydrogen and oxygen. So electrolysis means you're actually putting energy into it for it to occur. You're basically introducing electricity. So it's endothermic. It requires heat or an energy input. So if we were to go through the whole process here of calculating bond energies, the reactant is 2 H2O molecules. So we have 4 OH bonds for a sum of bond energies broken to be 1856. Then we get 2 HH bonds and 1 O double bond, which gives us a total bond energy of products to be 1362. And so when we take the sum of the bond broken minus the sum of the bond energies formed, we get a positive 494 kilojoules per mole. So it is indeed a positive delta H. Endothermic requires energy. Okay. So this is a quite involved way of determining the heat of reaction, delta H, and you have to know all of the bond energies and all the bonds present. But for small reactions with small size molecules, we can do this, okay? And we end up with a quantified measurable value of delta H. We will return for part 3 to look at another way to calculate delta H from an energy diagram.